Hello everyone, I am Alperen, fourth year student in Electrical and Electronics Engineering. In this video I will talk about my STAR project, Deep Knowledge Tracing with Student Mapping. My supervisor is Gözde Akar. First I will make a brief introduction and talk about LSTM networks and knowledge tracing concept. Then I will talk about my project in a detailed way, then I will make a conclusion. First of all, what's the aim of this project? The aim is to optimize online learning. Since coronavirus has affected many areas, including education, we tried to optimize the bad parts on online education. Guiding students should be student specific, and we should be able to give feedbacks to students specifically, and not only for students, we should be able to give feedbacks for teachers also. And we are doing it by combining online learning with deep learning. Deep learning is a cutting edge area in technology, and it can be applicable nearly all fields which requires optimization. The general architecture of our model can be visualized as follows. We track the student progress, we collect the data from students and give that data as input to LSTM model, and LSTM model produces outputs and we interpreted it to guide both students and teachers. What are LSTM networks and knowledge tracing? LSTM networks are special kind of recurrent neural networks which feed themselves. LSTM networks are long short-term memories, and they can be considered like in this figure. Every time, in each time step, it takes input and combines that input with previous state and produces a next output. The T is time step value, how many times the state is updated. It tells us that, and it uses the past state in each time step. And LSTMs are updated version of RNNs. RNNs are basically in this figure. There is a problem in RNNs, a vanishing gradient problem. The sequence, the time step does not tell us how fast we should look in RNN networks. With the help of some states in LSTMs and GRUs for get state, the model can specify how fast the model should look to produce the next output. With the help of this development, we are able to predict time step sequences in more detailed, in more tidy way. And the applicable areas are handwriting recognition, speech recognition, machine translation, and so on. Knowledge tracing is another area for LSTM applications. Knowledge tracing is not a new concept. Bayesian knowledge tracing was used in previous years, and deep knowledge tracing is occurred with the development of deep learning. It basically predicts the student's learning state, learning level, from looking at the time, looking at the sequence of students' answers to exercises. It simply predicts the probability of making the next question right for that student. This also shows the learning state of that student, and time is a crucial factor in that model, because student can forget the subject or make a progress in subject, so the correct sequences where they placed is very important. We should be able to interpret these sequences considering time also. Now, deep knowledge tracing with student mapping is our method for optimizing this process. Model workflow can be visualized as follows. First, we do input processing. In input processing, we take the raw output and turn that into stacked sequences. Each line is questions answered by students for a specific subject. Then these stacked sequences are padded to a specific length, and the model takes that input and produces an output between 0 and 1, clearly saying the learning state of student, which is also the probability of making the question right, making the next question right for that subject for a specific student. Input processing part can be visualized also in that figure. The input consists of hundreds of blocks like this. In that block, it tells us that the student solved 28 questions from the subjects in second line. There are 28 subjects, and the third line corresponds to the correctness values of this questions attempted. Then we split that data. We split the third line as a subject-specific manner. For instance, 5 questions in subject 30 are solved, and 1 for 34, 1 for 36, and 8 questions are solved from 44th subject. We stacked all the correctness values in subject-specific manner. Then we pad these values. The reason why we are padding is because model takes input with specific time step length. The batch is 7 in that example. There are 7 sequences, and the time step is 8 as the longest sequence, and the feature is 1 because we are concerning with correctness value only. The input shape is like this. After the model takes input, masking layer ignores the -1 values, and we are simply working with these datas, and LSTM layer predicts the next question, probability of that question being answered right, and it goes into dense layer, and the dense layer produces an output between 0 and 1. The outputs can be visualized as follows. The student 265 solved questions from 13 different subjects. X-axis length defines the longest sequence attempted, which is subject 1 for that student. And -1 values in padding make sense in here. The model ignores them and simply predicts next learning state nearly 0.5. And the last column is current learning state for corresponding subject, and that also tells us the probability of making the next question right for that subject. If it is close to 1, a subject is learned well up to now, and teacher can define a threshold and guide the students and advise maybe to study more on subject 1, 5, 44 and 123. Another advice may be to solve more questions from different subjects, and this is another input, another student mapping, 282. It's obvious that for that student he or she should study more, and different guidance will be made by teacher. From teacher's perspective, average of learning states and standard deviation of them can be analyzed. Every student's learning states for each subject are taken and computed the average. We can define a threshold and say that teacher should work more and teach more on the subjects below the threshold value, like these subjects in this figure. And in standard variation graph, we tested the distribution of learning states among class. If standard variation is high, we can conclude that students did not learn equally. Even though mean is high, standard variation should be considered. Teachers' aim should be to bring every student to same level. The subjects with zero value in both graph means no one attempted on that subject, and zero standard deviation with some value of average means only one student attempted that subject. Up to now, we worked with base model to produce these visualizations. However, the subject-based model can be implemented as feature works. The base model is robust and accurate. The accuracy was about 80%, but if there is enough data for every subject in data set, the subject-based model can lead to higher accuracies. However, for our data set, for instance, the subject 75 has very little data. It has very little data, so it is trained with very little data, and for hypothetical input, the color changes in mapping is very little. However, if there is enough data, like in subject 96, to train the model, the subject-based model can lead to very good accuracies, and it is more understandable mapping for that hypothetical input. This is the future work which may be modified in that project. In this project, we tried to create LSTM network to optimize online learning. We tried to combine online learning with deep learning. Modeling the learning in education is very critical things to optimize this process, and with the help of deep learning there are so many things to do, and this may lead to very good points in future research. Thank you for your attention.